Hi, my name is Shahnawaz. In this lecture, we are going to study the basis for our topology. But before that, uh, we have the following observation. So, as we mentioned in the last lecture, that if we have a set X, so on this set we can define more than one topology, and we give some examples of topology on X. I mean the discrete topology, the indiscrete topology, the cofinite topology, the countable complement topology, and so on. So on a given set X, we can define many topologies. Now there is this question. So if we have a set X, so let us make this a proposition. So let us consider a set X. So let X be a set, and so let Ti, where this I is in lambda, be any collection of topologies on X, be any collection of topologies on X. Then we claim their intersection is a topology on X as well. Then the intersection of these Ti's, where I is in the index set lambda, so this is also a topology on X. Now let us prove this. So first of all, to prove this is a topology on X, we have to prove it satisfies the three axioms of topology. So one can observe that the empty set and the X, they both belong to the intersection of these topologies. So they both belong to intersection of these Ti's, where I is in some lambda. The reason being, this empty set and X, they are in each Ti, since the empty set and X belong to Ti for all I in the index set lambda. So this is the reason. Now what we have to prove? We have to prove this intersection of topologies, this is closed under arbitrary union as well as finite intersections. So let us take any collection of sets in this intersection. So now let say Uj, where J is in some index set delta, be any collection of elements of this set here. I is in delta. Now we have to prove the union of this collection is also in this intersection. So this is what we have to prove. So first of all, note that since each Ti is topology on X, and this collection is in each Ti, it follows that, so since Uj, where J is in delta is a collection of elements. Since this collection is in the intersection, so it is in the in each Ti. So is a collection of elements in each Ti. It follows that then union of this collection, I mean union of UJs, where J is in delta belongs to Ti for all I in lambda, because each Ti is topology. Now if this is the case, if this is true for each I in lambda, so this is true for the intersection as well. So that is U of J belongs to delta, I mean the union of these UJs, this is in the intersection as well. So this I is in lambda. This means this intersection is closed under arbitrary union. Now to prove it is closed under finite intersection, so let u1 u2 through un be elements of this intersection. So I mean this is a finite collection. Now we have to prove their intersection is also an element here. So then u1 u2 through un belong to Ti for all I in lambda, because these ui's are in this intersection. This means these ui's are in this Ti for all I in lambda. Now since each Ti is topology, that means each Ti is closed under a finite intersection. That means if I look at the intersection of these elements, that is going to be an element of Ti for all I. So this implies intersection of these Ti's where this I runs from 1 to n. So this is, sorry, these ui's. So this is going to be an element of Ti for all I in lambda, because each Ti is a topology on X. So hence intersection of these ui's where I runs from 1 to n belongs to the intersection of these topologies where I is in lambda. This means that this intersection is also closed under this intersection of topologies is also closed under finite intersections. So this proves that this intersection of topologies is also a topology on X. Now let us define the finer and weaker topologies, or what we call the coarser topologies. So this is a definition. So suppose we have two topologies, say T and T prime. So suppose T and T prime be two topologies on a given set X. So if suppose if T prime contains T, we say T prime is finer than T. We say T prime is finer than T. and if T prime properly contains T, so and if T prime properly contains T, we say T prime we say T prime is strictly finer than T. We say T prime is strictly finer than T. We also say T is coarser than T prime or strictly coarser than T prime in these two respective situations. So let us write this down. We also say T is coarser than T prime or strictly coarser. Strictly coarser than strictly coarser in these two respective situations. Now what we mean by that, so here T prime contains T, so we say T prime is finer than T and this T is coarser than T prime. Now if this is the case, if T prime strictly contains T, then we say T prime is strictly finer than T and this T is strictly coarser than T prime. Now let us now define. So if we look at two topologies, I mean the discrete topology. So if X is a space, I mean a set, and we look at the topological space xt where D is discrete topology on X, and I look at X and the I where I is in discrete topology. Now this D means here, the discrete topology means here that this D contains all the possible subsets of X, and this I just contains the empty set and the X itself. So this topology over here is strictly finer than this indiscrete topology. So this is an example here. Now let us define the basis for a topology. So we have basis for a topology. So we have this definition. So let us consider any set, say X. So let X be any set. Now a basis for a topology, so a basis for a topology is a collection say fancy B of subsets of X, of subsets of X, and these subsets are called the basis elements, I mean the elements in B are called basis elements, such that, so we have two conditions here, such that for each X belongs to X, there is at least one basis element, say B, containing x. Containing this small x. I mean this is our set x, and this B is just the subsets of x. So we call this a basis if for any x in x, I mean if for any this small x in x, there should exist as a basis element B which contain this x. So this must be true for each x in x. And the condition second is that suppose there is some x, suppose or let us write this way, if x belongs to the intersection of two basis elements. So if x belongs to the intersection of two basis elements, say B1 and B2, then there must exist a basis element B3 containing x, and is contained in B1 intersection B2, and is contained in B1 intersection B2. I mean suppose we have this set x here, and suppose we have two basis elements, say this is B1, and suppose we have other basis elements, say B3, and suppose we have an element x here which is in the suppose this is B2, which is in the intersection of B1 and B2, then we call this base B a basis if for this element which is in the intersection of B1 and B2. So then there must exist an element, say small b, this B3 in B, such that this B3 contains this x and is contained in this intersection. So this is the intersection of B1 and B2. So this is B3 here. So the condition is that x should belong to B3 and B3 must be contained in B1 intersection B2. So then we call this B to be the basis of set x. Now there is some observations. So note that this B contains these basis elements, while this B is actually a subset of x. So this is this fancy B. Now if we look at the union of all basis elements, so if we look at this union, which is the union of all elements in this fancy B, so this is actually a subset of x, because each bi is a subset of x. So clearly this union is contained in x, since the reason is each b in B is contained in x. And this is the first observation, and this is the second observation. So what we say this B is actually a basis if for each element, say this small x in capital X, there is a basis element, say B, which contain this x. So this means that there is actually a correspondence between the elements of x and the basis elements of B. that means so since so if so let x belongs to x, then there exists b in b such that x is in b. So this is true for any x. So that means since there is one-to-one correspondence between each element small x in this capital X and the basis element is in b, that means this x can be expressed as a union of these basis elements. Then this x is contained in the union of these basis elements, where this little b is contained in, so this is in the fancy b, and this is the reason this is true for any x in b. So hence for each x in this capital X we have a basis element such that this x is contained in b and b is contained in x. Now if we combine these two observations, these two statements here, this means that, so hence this means this x is actually the union of these basis elements, where this b is in fancy b. Now we are going to prove that this fancy b, which contains the elements of which contain the elements which are subsets of this capital X, we are going to prove that this actually generates a topology. So if so we forgot to mention here, so if b satisfies, so let us write this down here. So if b satisfies these two conditions, then we define the topology tau generated by b as follows. So if b satisfies the two conditions, I mean these two conditions, condition 1 and 2, these two conditions here, then we define T, I mean we define the topology T, we define the on topology T generated by these basis elements, by the elements of B, as follows. Since we know that this T here, this contains the elements, now since we are going to prove this is a topology on X, so that means this T contains actually the subsets of X. Now to prove it is a topology on X, we have to prove this T satisfies the topology actions. So now here we define, so but we know that if X and tau is a space or topological space, then any element in tau is said to be open subset of X with respect to this tau, with respect to this T here. So here we define, so a subset U of X belongs to this T if for each X in U there exists B in this fancy B such that X belongs to B and this B is contained in U, then we say this U is a subset of tau, or this U is open with respect to this T. So so what we have to prove? We have to prove this basis actually generates a topology that we call this fancy T, and an element belongs to here, i.e. an element is open in X if for an element U is in T, or we can say an element U is open in X with respect to this topology if this is the case, if this is satisfied, i.e. if for each X in U there is some basis element B such that this condition holds, then we say this U is open in X with respect to this topology generated by the basis elements. Now let us prove this is a topology. So one should note here each basis element B is open in X, i.e. each basis element is in tau, because so to prove B is in tau, what we have to prove? For each X in X there is some base element B which is contained in B. So if we replace U by B, this is still valid. That means each basis element is actually in tau, T I mean. So let us make this proposition. So the collection T generated by the basis B of X is a topology on X. And a subset U of X is open if this is the case. So let us prove this. Now first of all we have to prove both the empty set and the X are the elements of this topology. Now to prove this empty set is open, i.e. to prove this empty set is in this T, what we have to prove? We have to prove every element of this empty set satisfies this condition, but there is no element in this empty set. That means this is open in the sense that there is no point in this empty set for which this relation is not true. So this is open in that sense. So indeed this empty set is contained in tau, i.e. this empty set is open in the sense that there is no point say X in empty set for which the relation that X belongs to the basis element B and B is contained in U is not true. So we are not able to exhibit an element in the empty set and to show for that element and this relation is not valid. So if that would have been the case, then we can say this is not open, but we are not able to exhibit such an element for which this relation is not true, hence this is open. also x belongs to tau. I mean it is open, so we have to prove it satisfies this relation. So this is open. The openness of x follows from the first condition of the basis, I mean the fancy b. So the reason for this is that since for each x belongs to x, there exists b in b such that x is in b, and this is not fancy b, such that x is in b and b is contained in x. So this is actually the first condition of the definition of the basis. So we say u is in tau if for each x in u there exists b in b such that this is true. Now to check whether x is in tau, we have to prove for each x in x there exists b in b such that this condition is true. But this follows from this first condition here, that is for each x in x there is at least one base element b containing x, and this b is obviously a subset of x. So let us write down in bracket which follows from the definition of this fancy b. So hence it is open. So first action is satisfied. Now to prove it is closed under arbitrary unions, so let us take a collection of subsets of this T. So let u alpha, where alpha is in some index set gamma, be a family or a sub collection of this tau. We have to show that its union is also in tau. So this is what we have to prove. So we write this expression over here. We denote this union by u. So we have to prove u, which is equal to the union of all these u alphas. We have to prove u is also an element of T. So u will be an element of T if for each x in u there is an element b in b such that x is contained in b and b is contained in x. So we have to prove for each x in u there exists some b in b such that x belongs to b and b is contained in T. This is what we have to prove. So let x belongs to, not T here, u. So let x belongs to u. So if x is an element here, then x is in some u alpha, for some alpha in lambda, because it is in the union, so it has to be in one of the u alphas. So then there exists some index alpha in lambda such that this x is in u alpha, but u alpha is in tau, and u alpha is in tau only if this condition is satisfied. So then there exists some b in B such that x belongs to B, which is contained in U alpha, and U alpha is contained in U because it is one of the U alphas, so it is contained in U. So what we proved for this x, there is some basis element such that x is in B and this B is contained in U. So hence U is open, i.e. hence U is in T. Now we have to prove it is also closed under finite intersection. I mean, we have to prove this T is also closed under finite intersection. Now it suffices to prove it is closed under intersection of two open sets. So let us take two elements U1 and U2 in this T. We want to show that their intersection is in U as well, in T as well. So now to show that this intersection is in T, what we have to prove? We have to prove for any x in this intersection there exists a base element B such that x is in B and B is contained in the intersection. So let x belongs to U1 intersection U2, then x belongs to U1 and x belongs to U2. Now U and U1 and U2 being elements of this T, then it satisfies this condition here, because an element is in an element U is in T if for any x in U there is some base element B for which this condition is true. So then there exists B1 in B and B2 in B such that this x is in B1 which is contained in U1 and x is in B2 which is contained in U2. Now here we have this B1 here, this is B2 here, and x is there in the intersection. Then by definition of basis we have a base element B3 such that x is in B3 and B3 is contained in intersection. So then by definition of this fancy B, there exists B3 in B such that x is in B3 and B3 is contained in the B1 intersection B2 but B1 is in U1 and B2 is in U2. This is, so let us write this down here. So this is our U1 and this is our U2, and in U1 we have B1 here and in U2 we have B3 here. So this is B2 here, and in B1 intersection B2 we have, let us make this intersection a little bigger. So this is B1 this is B2 in b1 and b2 we have this basis element b3 which contains x. So this x is in b3 and this b3 is in b1 intersection b2. This is the b1 intersection b2, this portion. But this b1 intersection b2 is contained in the u1 intersection u2, which is this intersection over here. So this is contained in u1 intersection u2. So this means for x in this intersection we are able to find a base element b3 for which x is in b3 and b3 is contained in u1 intersection u2. So this implies this u1 intersection u2 is also an element of tau, this fancy t, and by induction this implies finite intersection of any number of subset elements of this t is also an element of t. So then by induction it follows that if u1 u2 through un are elements of tau, then so is their intersection. This proves the third axiom. Hence this T satisfies all the topology axioms. In other words, this T is a topology. So hence T is a topology on X, and this topology is generated by the elements of B, i.e. the basis elements.